in some sense, the more interesting part of the spectral analysis is when you try to analyze from the spectral side the non-diagonal matrices, and that's what we're going to focus on. And here's one example of the non-diagonal matrix. It's the second example on this slide. It's the example from the yellow book. It's a 3 times 3 matrix this time, non-diagonal one. Here's the entries of my matrix: 0, 1, 0, 0, 0, 1, 20, negative 24, 9. It's a 3 times 3 matrix with real entries. The example goes to ask, verify that the vector x, like this, 1, 5, 25, vector x like this, is an eigenvector of this matrix. So what we have to verify, we have to see that we can produce a number. We have to produce a number. We can produce a number such that we can produce a number lambda such that this identity true for this matrix A and this vector x. That's the key identity linking eigenvalue, eigenvector, and the matrix. Well, given that we have a candidate for the vector already, just verifying such an identity is an easy thing. All we have to do, we have to compute the left-hand side and then try to guess the number lambda. Here's my computation. Look at this. If I compute the left-hand side, A times x, well, here I'm being very detailed. I gave you very detailed computation. If I multiply this matrix A with such a vector x, here's my multiplication. First line, 0 times 1, 0 times 1, 1 times 5, 0 times 25. It's the first line of my result. Second line, again, very detailed multiplication. 0 times 1, 0 times 5, 1 times 25. It's the dot product of the second row and this vector. And the last one, and that's the last one. It's the dot product of the last row and this vector. The first two are easy, right, because they are dominated by zeros. The only non-zero one is 5 and 25. The bottom one, you can use your calculators, or if you're a little bit more smart than just pushing the buttons on the calculator, you can see that you can common factors here, 5, 5, and 5. If you factor out this common factor, the expression in this in third component becomes like this, right? 5 gone from here, 4 left. 5 gone from here, negative 24 left. 5 gone from here, 5 left. This is easy arithmetic. It's a 45 take 20. It's 25 times 5. So my vector is like this. 5 from here for the first component, 25 from here for the second component, and here we have 5 times 25 in this bracket as we computed before. Here it is. If you factor out 5 out of this vector, you will end up with the vector x, and that's my identity verify. So this vector is indeed eigenvector, and we identify the associated eigenvalue. It is 5 right here. So this example goes to show you that when you have a candidate for the eigenvector, finding the associated eigenvalue, it's just a very simple arithmetic. You just take the left-hand side, compute it, and then try to guess the scaling. Try to guess the scalar lambda which works for the identity. Any questions?